Hi, my name is Felicia and I'm a senior data scientist in Adarga. And today with my colleague Sebastian, who is a machine learning engineer, we're going to talk about how we set up a system for named entity disambiguation and discuss the scientific and technical challenges we faced. We're also going to present a bit about our learnings. So in more detail, our agenda for today. First of all, I'm going to introduce Adarga, who we are and what we do. Then I'm going to discuss a bit about named entity disambiguation, so the theoretical background, the challenges and the methodologies involved. And then Sebastian is going to take over and talk about developing our new model and training infrastructure. And he's mainly going to cover the data science and engineering challenges involved. And he's also going to talk about our experimental spike around using SentenceBird embeddings. And then he's just going to close off the presentation with a conclusion. So, Adarga, who are we? We are an NLP company with focus on defense and security. We were founded in 2015, and we currently consist of 63 employees, most of whom are data scientists and engineers. We mostly work in a cloud-native architecture, so Kubernetes and Docker. And the pipeline we're going to present today is a spaCy-based named entity recognition and disambiguation pipeline. And before we get into the implementation side of things, I'll just start off by introducing our problem domain. So we're working within the field of information extraction, and we're actually trying to extract information, structured information from unstructured text. And an example of such structured information is a named entity. And an entity is a real-world object, such as a person, a location, or organization that can be denoted with a proper name. And ultimately, the task of detecting and classifying these entities into some sort of predefined category set is called named entity recognition. And actually, named entity disambiguation comes into play when it's actually unclear or ambiguous which entity is being referred to in a piece of text. And more formally, named entity disambiguation or entity linking is the assignment of a knowledge base identifier, be it from Wikipedia, Wikipedia, or something more custom, to a named entity. So just looking through a simple example, London is Europe's largest tech hub. For a human, the context may be sufficient in resolving, which exact London is being referred to here. But for a machine, the assignment of a unique identifier is actually explicitly necessary. It can't really know that in that sentence, London is actually the one in the United Kingdom. And this is quite a challenging problem. This sort of disambiguation is especially useful in fields that need to extract abstract representations from unstructured text for downstream tasks, such as like search or recommendation. And you can expect that this text coming into those tasks is not going to be gold standard quality. It's going to be colloquial speak. It's not always going to be great quality. So we really need to work hard to resolve it. And broadly speaking, there are three categories of challenges that we had to deal with. So first of all, and this is generally for most NLP problems, first of all, there's ambiguity. And ambiguity with a capital A is actually a thing in linguistics. It's a type of meaning in which several interpretations are actually possible. So in our case specifically, we had to deal with named entity ambiguity. And this can be broken down to two subtasks. First of all, there is a case in which multiple entities may refer to one alias. And in linguistics, this is called polysemy. And here we have an example of like 3 different Londons, all based in different locations. And then there's also the case in which multiple aliases may be used for one entity. And this is also called name variation. And in this case, it could be something like USA, America, United States of America, or just the US used to represent the United States, which is yet another reference to that named entity. Second of all, there's also the fact that we're entirely dependent on the accuracy of our underlying named entity recognition system, which is actually defining the entities themselves. And it's really, I guess, there's the age-old garbage in, garbage out problem. So if your underlying system is not performing well, you can't expect the system following it to do better. So we're really dependent on that sort of performance. And finally, we also need to note that an entity's relevance and popularity is temporally sensitive. So it's sensitive to time and may change due to short-term events, topical events, or even just the natural evolution of language itself, just because, word meanings change over time. And in terms of methodology, setting up a named entity disambiguation system is relatively straightforward. Ultimately, we need a system that is capable of mapping some sort of alias or just an ambiguous reference to an entity in some context. To the named entity it refers to. And this can be done using a combination of graph-based and text-based approaches. And the idea here is to make use of knowledge graphs that have been enriched with additional textual features and the text corpora that were used to build those knowledge graphs themselves. And the idea here is to use, just using a knowledge base, we computed the prior probabilities of an alias referring to a specific entity. And then we also computed the context similarity of the alias and the descriptions of the entities themselves. And finally, we just combined the sort of scoring to determine the semantically closest target entity. And this sort of combination was just done with weighted averaging. So just starting off with the knowledge-based approach, the graph approach, the idea here is to calculate the prior probability of how often entities and aliases co-occur. So how likely an alias is meant to refer to an entity. And specifically, these priors are calculated from connections, in our case, Wikipedia. It could be some other knowledge base. For a given article, we just take the hyperlink strings to represent the alias that links to a unique entity's web page. We take that to be the unique identifier. And then the conditional probability of an entity given an alias is then calculated by taking the relative frequencies from Wikipedia. So obviously, given Bayes' theorem, if an entity is infrequent enough, the prior is penalized. And here's just a worked example of this methodology. So we have an example text. London is the largest city in Western Europe. While London's tourism industry is booming, its financial industry is more important. There are other cities with the same name, such as London, Canada, or London, Ohio. And as you can see, there are just 4 mentions of London. And we're just assuming, using Wikipedia, that these references have already been resolved. So we know which London they're actually referring to. And just if we do a simple count, we can see that 2 out of 4 of the mentions reference of the London mentions actually refer to London, the UK. So we can assign a probability of 0.5. And then I guess accordingly, we can assign a probability of 0.25 to London in Canada and London in Ohio. And now just moving on to context similarity. This is our text-based approach. And the idea here is quite simple. It's just we just encode text as a vector representation. In the past, you would probably use something like TF-IDF, but nowadays just embeddings. So yeah, we just encode entity descriptions from the knowledge base, and then we also encode the sentence that the entity is found in during inference, and the entity, the reference of which we want to resolve. And the idea here is to just calculate similarity metrics between these encodings. For example, using cosine similarity, that tends to be the go-to choice for text. And then we just pick the most similar candidate. And again, here's a work example. So let's say we have 2 Wikidata descriptions, one referring to London in the UK and one referring to London, Canada. So the first one, capital and largest city of the United Kingdom. Straightforward enough. And then the second one is city in southwestern Ontario, Canada. And then we actually have our target, which is the sentence that contains a reference to an entity which is unclear, and we want to disambiguate London. So London is the largest city in Europe. And if we just embed all these sentences and then just compute their cosine similarity, we can see that the highest score is assigned to the one that refers to London, the UK, which is right. And I guess just to bring everything together, from an architectural point of view, our disambiguation system consists of 2 main components. The first one is obviously the knowledge base, which is a database of alias and entity combinations and their, according embeddings. There are 2.5 million entities in our base, and three times that number of aliases. And its construction parameters, which were mostly set up to denoise the system and ensure efficient performance, included the minimum number of alias to entity links, the minimum number of entity frequencies, just to ensure that the long tail of our data didn't skew our results. We also included maximum number of entities per alias to ensure that very densely connected aliases were penalized. And finally was also like the embedding they mentioned, which was used by the entity linker just to assign embeddings to each entity from its description. And finally, there's also the entity linker, which is a neural net, and it's an encoder. So it basically embeds our entity descriptions and target sentences. And then it's just trained to improve and maximize semantic, well, it's trained to predict the semantically closest entity and sentence pairs given their embeddings and the cosine similarity metric. And ultimately, the priors from the knowledge base and the context similarity from the entity linker are combined to output the most likely entity for an alias. And just to close off, I'll briefly introduce the challenges we faced in creating a new model. And then Sebastian is going to talk about actually how we did everything. So we had to deal with three main problems. So first of all, we had to figure out a way to include new information into our system. And, you know, for example, given there's been a big ongoing event, COVID-19, and obviously when it all started, the knowledge base didn't include any references to it. So we had to figure out a way to constantly update our knowledge source and just to reflect the global information climate. Then we also had to semi-automate the entity linker retraining, just because we had new data coming in all the time and we had to keep up with the trends and also keep improving our relevance and our performance. And finally, we just given our constantly shifting and just to keep into account the dynamic nature of our data estate, we had to figure out a way to keep up with the new data influx and just retain our accuracy scores. So I guess this is also you, Sebastian.
Thank you, Felicia. Okay, now we'll go a bit more into the specifics of what we did. And I phrase this in a diagram a bit like a journey of where we're going, where we came from. So we started off with a trained spaCy entity linker MVP. And now based on these challenges that were given to us, include new information, retain accuracy, we have two big things that we had to do. The one thing is update the knowledge base with information from Wikipedia and Wikidata, so new information. And the other part is the automation of the entity linker retraining if we get new data, and to set it up so everybody can run it in a cloud environment, plus in an environment that is not OS specific, but in Docker. So the first part is the data science part in updating the knowledge base, where we identified three main data science challenges. The first one being parameter estimation, because there wasn't, not everything was documented when the MVP was being done. So retaining accuracy when updating the knowledge base is not easy if you don't have all the parameters. The second one is benchmarking. It's not really related to updating the knowledge base, but in my opinion, very important. If you want to deploy something new, you have to benchmark. And the third one is embedding dimensions. So in how many dimensions do we embed the descriptions of the entities in the knowledge base, and also later in inference. And we can see that this will be heavily influenced by the engineering constraints. So the first topic is benchmarking, and in my opinion, this is a topic that's very important, because why do we exchange a new model if we don't know that the new one is better than the old one? So you should always have some form of estimation if the new model is better. Fortunately for our task, spaCy also gives us a test set based on Wikipedia articles, but because we are in the defense and security industry, this does not really reflect a good or is not a great benchmark for our customers or our product. So we started, while doing all the training, we started developing a custom benchmark and also architecture for creating this custom benchmark. So once we have this set up, we can move to a more specific benchmark. So the takeaway from this is always do benchmarking before exchanging a model, even if it's just A/B testing or some form of it. But if you have hard numbers, that's always a win, especially if you have to sell it in the business. The first part of creating the new knowledge base was estimating parameters, and I also included data provenance here. And like I said earlier, the MVP results were hard to reproduce because we did not have the parameters documented, but we had to use some heuristics to do so. For the A&E links, so entity alias links, and the minimum number of entity frequencies, you could elicit lower bounds from the previous knowledge base if you queried the informations. So this wasn't perfect, but you could get a good estimate in. But we always chose to be more inclusive and allow for a bit more noise rather than cut off some things that might have been identified correctly but were too infrequent. So allow for the tails of the distribution. And the maximum number of entities that Felicia presented earlier as one of the parameters were easily elicited from the previous database, because you could query an alias with a lot of entities, like London, for example, which has more than 30 entities linked to it in Wikipedia, and just see where it's cut off, which was 20. And one word on data provenance here, because if you want to retain the accuracy when retraining a model, it's great to have all the parameters from the old one documented somewhere. So now we did that, did it in Confluence to document the parameters for knowledge base and entity linker, and also storing the data used for training, also the files of knowledge base and your whole model in some cloud storage is a great thing to do. And since MLOps became a fairly big thing in recent months or years, that's also part of that, to always know where your model comes from and how you go towards it in the future. Then the last part of the data science challenges was embeddings. And spaCy uses glove word embeddings, 300 dimensional, and they are reduced into sentence embeddings. Generally, we ask, okay, we want to retain as much similarity or semantic information as possible when choosing embeddings. So why, in this sense, did we cut down from word embeddings, which is 300 dimensionality of every word, into 64-dimensional sentence embedding? This shouldn't be the case if we want to retain as much information as possible. So why did we do this double loss of semantic informations? And we have to do that because there's a trade-off that I will talk about a bit later in the engineering part between what we want to do in data science, or how good our models in data science are, and what we can do in a production environment, because we are definitely constrained in engineering space in this particular example, which is shown in the next slide. The engineering part of our presentation will first go into the embedding dimensions, just as I presented it now from a data science perspective. I will do so from engineering constraint perspective, and then go into how we set up the retraining architecture for the entity linker. The engineering constraints, as a follow-up from the slide in data science and on embeddings before, are quite considerable. Generally, we'd love to have a high embedding dimensionality to capture all the semantic information we can, but in practice we are blocked by engineering constraints. One of them is that we need to hold the knowledge base in memory, and a knowledge base can be really big. Generally, in our serverless architecture, you can, in production, if you deploy it in Kubernetes or VMs or however you want to do it, you can adjust for that. You can just adjust for more RAM, but it's costly, and development is normally not being done in a cloud environment. We all do it now on local machines. Most businesses do it on local machines. And if your knowledge base is massive, you need maybe 20, 30 gigabytes of RAM just to host it. You can't do that locally. So you have to have a cutoff point in some sense. An example here is our old knowledge base, which has had 2.5 million entities. And with a dimensionality of 300, if we keep that dimensionality from Glove, we would have a size of 6 gigabytes to be held in RAM. Most laptops nowadays can do that, but then if you go higher in dimensionality, or as with the new example, we have more entities, this gets infeasible really quickly, especially if you use models that have high dimensionality generally, like BERT with 700x. So this is a major constraint of why we chose, or why we had to cut down on dimensions. Docker is a containerization tool. Not going to go into it that deeply. It's just used to have something that is generally reproducible and operating system agnostic. So it doesn't matter if you run it on your Windows or Mac. You choose an operating system, you choose which version of Python you install, which libraries you install, and everybody can run it, because it knows what it has to have to run it. So it's easily reproducible. There won't be any errors. Oh, I don't have this library. It doesn't work with that version. So you just have a Docker file with all that, and it has an entry point, which is a Python executable to train the entity linker. And you can set parameters by using environment variables, and you can get the data and the knowledge base you need from our cloud storage to do that. And we set it up that the model is also written directly into the cloud storage. So an easy way to reproduce it for anyone who comes after me or who wants to do it. This is being done in a containerization environment called Kubernetes. It's not that important to know what it does. It just runs the Docker image basically to do the training job. Because we don't have orchestration going on for just this Docker file. For the entity linker retraining, the default values that spaCy suggests are 160,000 texts to train it on in the Similarity, the cosine similarity that Felicia talked about, which is a lot. So there was another engineering constraint here. How do we train it? If we hold all this data in memory, it's going to be massive. It needs over 200 gigabytes of RAM to hold it all in memory. Or you do lazy loading and go for a magnitude lower, maybe 20 gigabytes of memories while training. You can see both numbers, even though you cut down with lazy loading, are too big to be run in most laptops if you don't have nice performing ones or large RAM ones. This was done in Kubernetes, for example, because we are also a company that has all orchestration in the production in Kubernetes. So it was the natural place to be. So you could tie this all in. And what I said before shows a large trade-off between speed and cost in this case. If we do it the lazy loading way, it would probably take around 4 weeks for us to train the model in the current environment. And if you do it in a fast way, it takes a couple of days. But also you have the cost element of getting a massive node to run it on. We decided, because entity linking, the world doesn't change as frequently as every couple of days, it would be okay to just do it every couple of months, the retraining to incorporate new data, fine tune it a bit. So we chose longer training and the lower memory option because of the engineering constraints. Then this was basically what we did. Then we had our new model, we had a new knowledge base, and we had a new architecture of how we retrain the entity linker model with Docker and Kubernetes. That is well done. We were happy, but we thought, are there a couple of quick wins when we could improve our F1 score with the entity linker model? And we were thinking about using more informative entity descriptions for knowledge base embeddings. Felicia earlier presented the ones for London, which basically just says it's the capital of the United Kingdom. It's not super informative if you want to compute contextual similarity, But for that, you would have to invest more engineering efforts into getting descriptions, for example, from Wikipedia instead of Wikidata. So we thought, no, it's a bit too much for now. Let's set it on the back burner and do something else. Then the second point, parameter optimization for entity linker. I just told you that it takes ages to run, a couple of weeks at least. So optimizing parameters here is not that easy. So we also discarded this for now. And the third part is possible, optimizing the weights in the weighted average between prior and context. We do have the data for that, but you would need to set up a new training framework to do that. We also thought we might do that later, but not for now. And the fourth point, replace the entity linker model that we now set up an architecture to retrain. This is not something that I would do lightly, but I stumbled across a SentenceBird pre-trained model that is trained on context similarity and thought this might be really good to do that. So just trying it out as Spike, we went and implemented, got rid of the CNN, spaCy-CNN, and replaced it with SentenceBird. I linked it in the sources later. You could pre-train your own model, and they also have a pre-trained version. And this is fine-tuned BERT on contextual similarity, which is exactly what we were looking for in this task. And you had to apply it to both creating the knowledge base and doing inference in as the linker replacement, basically. And this showed us again, we have this constraint of high dimensionality. Being a BERT model, it had a dimensionality of 768 dimensions, which is very large to be held in memory. It's around probably 20 gigabytes all in all, which is too hard to do locally, and also set engineering constraints during inference, because in the real world, in our industry, we need to match some performance. And BERT is a massive model with a lot of parameters going into the millions of parameters, which makes inference on normal CPU slow. Even using GPU, it's too slow compared to our current architecture. So we did see an increase in the F1 score using SentenceBird as compared to this spaCy-CNN model that we trained. But the constraints were also considerable that I just mentioned. So even though we saw that small improvement, which might just be a statistical fluke because it's so small, it also shows that the prior probabilities are much more important than the context similarity when evaluating the model. We decided to keep our previous architecture and not go for this model, even though it increased the F1 score, because it doesn't actually fit in our engineering environment as is. So things to take away from this is definitely that we did get a better model both ways with the retraining and the SentenceBird with up-to-date entities in a knowledge base, set up a new environment to retrain this more easily, and we could maybe in the future implement some BERT solution, but at the moment the trade-off between data science and engineering in forms of constraints in embedding space and constraints in inference were just too much to do that. So we decided to not go for the higher accuracy, but for something that fits into our architecture in our engineering environment. That was it from us. Thank you so much for listening. And if you have any questions, feel free to ask them. Thank you.